Scaling large language models hits a strict mathematical wall. As sequence context lengths extend, the computational cost grows quadratically rather than linearly. The immediate trap here is physical memory. To process a sequence, the model must store the past context in a key value, or KV, cache. As context windows push toward 1,000,000 tokens, that cache rapidly exhausts standard VRAM limits. The industry standard solution is brute force. Handling ultra-long contexts typically requires linking massive, power-hungry hardware clusters just to hold the memory state. DeepSeek-V4 introduces a structural anomaly that bypasses the quadratic bottleneck, maintaining high-performance reasoning with a fraction of the standard memory load. This chart shows the single-token inference flops for the V4 architecture. At the extreme 1,000,000 token mark, the V4 Pro model operates at just 27% of the computational cost of its predecessor. This second chart shows the physical footprint required for that context. The accumulated KV cache size drops to 10% for the Pro model and 7% for the Flash model. These metrics represent realized efficiencies running natively at a 1,000,000 token sequence length. Normally, cutting 90% of a model's memory footprint requires aggressive pruning that guts reasoning capabilities. V4 maintains state-of-the-art performance across coding, math, and knowledge tasks. Achieving this anomaly required tearing down the traditional homogeneous dense attention mechanism and replacing it with an asymmetric mathematical structure. DeepSeek-V4 runs on an asymmetric, three-pronged hybrid attention architecture. The first pillar is Compressed Sparse Attention, or CSA. This layer physically shortens the sequence representation, compressing every 4 blocks of KV cache into a single dense entry. To prevent information loss during compression, a low-rank mechanism called the lightning indexer evaluates incoming query tokens against these dense blocks. The indexer applies a strict sparsity filter. It scores the blocks and selects only the top K entries for the actual attention computation, while the remaining entries drop out of the path. The second pillar is Heavily Compressed Attention, or HCA. This is engineered for extreme density, crushing chunks of 128 tokens into single nodes. Unlike the first pillar, HCA skips the indexer and sparsity filter. It processes its highly condensed sequence densely to preserve broad, long-range contextual awareness. This aggressive compression creates a causality gap. When queries only look at condensed blocks, they struggle to resolve fine-grained details in their immediate local vicinity. The third pillar covers that blind spot, a parallel branch called Sliding Window Attention, or SWA. SWA acts as a local high-fidelity safeguard. It retains the raw, uncompressed KV entries for the most recent tokens, bypassing the compression stops. By interleaving sparse routing from CSA, the extreme density of HCA, and local precision from SWA, the architecture overcomes the flops bottleneck while maintaining complete data awareness. Stacking dozens of these highly complex, three-pronged hybrid layers introduces a severe and constant risk of catastrophic numerical instability during the training process. To handle this complex routing, the width of the residual streams must expand. In deep networks, this often causes gradients to explode, leading to signal collapse. DeepSeek-V4 implements a mathematical safeguard called Manifold Constrained Hyperconnections, or MHC. MHC forces the residual mapping matrix into a specific structure. It constrains it to a doubly stochastic manifold using the Sinkhorn-Knopp algorithm. The algorithm iteratively normalizes the rows and columns until the matrix reaches a state where every row and column sums perfectly to 1. This configuration bounds the spectral norm to a strict maximum of exactly 1. A bounded spectral norm ensures the transformation is non-expansive. It prevents an error signal from multiplying exponentially and destroying the network. To complement this, the model uses the muon optimizer, which runs Newton-Schultz iterations to aggressively orthogonalize the weight matrices. MHC is the load-bearing ironwork. Without mathematically guaranteeing a non-expansive residual stream, this hybrid attention framework would collapse during pre-training. The final systems engineering hurdle is mapping this abstract math into the physical GPU. Standard memory allocators assume every token requires the same amount of cache space. V4 compresses some tokens by a factor of 4 and others by 128. This asymmetrical geometry breaks standard memory management. The solution is the heterogeneous KV cache layout, which splits the VRAM into two distinct architectural zones. The first zone is the state cache. It manages the high-frequency, uncompressed data used by the sliding window attention blocks. The state cache also serves as a holding buffer. It catches pending tail tokens and stores them until enough accumulate to trigger a compression event. Once compressed, the data drops into the main KV cache zone, which permanently stores the outputs from the sparse and dense attention layers. To keep the computational kernels running at peak efficiency, these cache blocks are strictly aligned to the least common multiple of the compression ratios. The engineers apply one final low-level multiplier, FP4 quantization-aware training. The activations for the Lightning indexer are stored and multiplied in 4-bit precision. This doubles the processing speed of the sparsity filter. The 10% memory paradox is achieved by sculpting the VRAM layout to align with the asymmetric geometry of the hybrid math. DeepSeek-V4 delivers massive capability within a fraction of the traditional computational footprint. This chart shows the model's capabilities. The blue hashed bars track V4 Pro Max, leading open-source models in core reasoning, coding, and knowledge evaluations. Those benchmark scores are secured while simultaneously collapsing both inference flops and KV cache requirements. This performance is enabled by algorithmic sequence compression to cut flops. It is supported by manifold-constrained hyperconnections to lock in mathematical stability, and it physically operates through a heterogeneous memory layout that maps asymmetric data into VRAM. DeepSeek-V4 proves that relying on standard dense attention is a complete dead end for ultra-long context scaling. The future of test time scaling belongs to architectures that reconfigure the physical geometry of information storage.